Hello, and welcome to Lesson 16 of this Introduction to Calculus with Wolfram U. The topic of this lesson is Maxima and Minima. So let's begin with a brief overview of the lesson. So many mathematical problems involve getting the best solution for a task. In fact, people would use mathematics when they really do want the best solution for a task. And there's a word for best solution. It's usually called optimal or optimal solution. And the whole process of getting such a solution is called optimization. Okay, so as an example of optimization, let's take this function f of x and plot it. The plot is a downward opening parabola, and the highest value of this plot is clearly at 0, 3. So in this case, our notion of best or optimal is the highest value. And typically, one wants to talk about maxima and minima in various problems. So the goal of this lesson is to develop a process for finding maxima or minima for different problems using derivatives. So various people use optimization in different ways. So for example, if you run a business, then clearly what you want to do is to maximize your profit and minimize your cost. Even a plant knows that it must grow in such a way that it obtains the maximum amount of sunlight. A GPS system is designed to get you to a destination in either the shortest amount of time or distance. So in general, you have optimization problems which involve either finding the maximum or the minimum. And so differential calculus is really an excellent tool for solving these optimization problems. In fact, that's how the subject arose in the works of Fermat and other mathematicians. So let's now go ahead and talk about the notion of an absolute maximum or minimum. So a value f of c is an absolute maximum of a function if its value is greater than or equal to every other value for the values in a certain set, capital D, where D is called the domain. So when I say maximum and I say absolute maximum, I mean the very greatest value of a function. And similarly, if one says absolute minimum, you mean the least value of a function on a certain set D. So for example, if you take the sine function, clearly its maximum over here at pi over 2, where it's got value 1, and its minimum at 3 pi over 2, where it's got the value negative 1. Now, another term used for absolute maxima and minima is global maxima and minima. So when they say absolute, they mean the same thing as global. Okay, and together these maxima and minima are sometimes called the extreme values of the function. Now, in this case, we are lucky we had an absolute maximum and an absolute minimum. But in general, the best that you can hope for are so-called local maxima and minima. So for example, here is a function, a cubic function, and you can see quite clearly that this graph has got local maxima and minima. So that's a local maximum over here, and that's a local minimum over there. But if you go far away enough, the values will go up or go down dramatically. So the idea of a local maximum is that you have a value f of c which is more than other values for x near c, and similarly for local minimum. So near depends upon the function, of course, but that's a nice way of talking about maxima and minima by using the local definition rather than a global definition. Now, in the case over here, there is a local maximum at that point and a local minimum at that point. We'll see that quite shortly. And of course, if you have an absolute maximum, that's clearly a local maximum, and if you have an absolute minimum, that's clearly a local minimum. So the fact that you have absolute maxima minima is very special knowledge, much better than having local maxima or minima. Okay, so things could go wrong or be different in some case. So for example, if you have the constant function, like over here, the constant function 5, then clearly every real number is an absolute maximum and minimum. On the other hand, if you have the cubic function over here, then you have neither an absolute or a local maximum or minimum everywhere. So these are very special cases which are worth remembering as we talk about maxima and minima. Namely, that you could have a situation in which either you have everything being kind of optimal or nothing being optimal. Okay, so now the question is, how do we find these extreme values? But even before talking about that, we need to figure out some conditions under which one can guarantee that there are extreme values. And this is what's called the extreme value theorem. So what that does is it gives you conditions for when a function is guaranteed to have extreme values. So it says that if you have a function on a closed interval and that function is continuous, so you have a continuous function on a closed interval AB, then that function will attain an absolute maximum and an absolute minimum at some numbers C and D in that interval. So as long as you have a continuous function and a closed interval, you are fine. So for example, I have these three plots over here, and the black dots will indicate that that side of the interval is closed, and the white dots or the blank dots will indicate that you have an interval side which is not closed. So in the first example, you see you got two black dots, so that's a closed interval, and clearly you have a continuous function. There are no breaks in the graph, and you have an absolute minimum over here and an absolute maximum over there. So that's the first example. It attains an absolute maximum and minimum on the interval. On the other hand, the second example is not in the scope of the discussion today because you have over here a function which is not continuous. You can see over here that it's got a break in the graph. So the theorem does not apply, and you do not need to worry about whether there are absolute max or minima. But of course, in this case, you actually do not have them because the function seems to go off to minus infinity over here and plus infinity over there. The last example is again not quite relevant because here you have an open interval. So because the interval is not closed or it's open, therefore you cannot guarantee anything from the extreme value theorem. But in fact, in this case, there is neither an absolute maximum minimum precisely because of the issue with missing endpoints. Okay, so the question now is, how do we actually find these extreme values? And the best tool we have for this is Fermat's theorem, given by Pierre de Fermat a long time ago. So what that does is it lets us find local maxima and minima. And what it says is that if f has a local maximum minimum, then its derivative at that point must be 0. So for example, if you look at the earlier function, then the claim is that it's got local maxima and minima over here and there, and you can check that with the derivatives at those points. They're both 0, so Fermat's theorem will say that that's the condition to be satisfied for local maxima and minima. Okay, so there are a few things to remember about Fermat's theorem, that the converse is not true, and it's not true in a few ways. So for example, you have a function over here, the cube function, and clearly you have a horizontal tangent over here. The derivative is 0, and yet there are no maxima or minima. So the theorem merely says that if you have a maximum minimum, then the derivative must be 0. And here's another example, which is the absolute value function, where you do have a minimum, but then the derivative does not exist at that point. So Fermat's theorem must be used with caution, but it in fact is a very powerful theorem. So Fermat's theorem is really talking about what are called critical numbers. So when you want to look for maxima and minima, you need to look at what are called critical numbers. So what's a critical number? Well, a critical number is a number where either you have a zero derivative or the derivative does not exist. So for example, the cube root function has a critical point over here because the derivative is not defined there. And of course, the local maxima and minima are good places to look for critical points. So with all that information, we are now ready to put together a method for finding absolute maxima and minima. So that's what is called the closed interval method. And what it says is that to find the absolute maximum and minimum of a continuous function on a closed interval, you first of all find out the critical numbers, find the values of the function at those critical numbers, then you work out the value at the endpoints, and then the largest of all those values is the absolute maximum, and the smallest value will be the absolute minimum. So as an example, here's a cubic function. You find the derivative, set it equal to 0, and figure out that 1 is a critical point. Add that 1 to the list 0 and 2. So you've got to look at 0, 1, and 2. So 0 and 2 are the endpoints of the interval. 1 is a critical point, and you find that the minimum value occurs at 1, and the maximum value occurs at 2. So you have an absolute maximum at 2, 2, and you have an absolute minimum at negative 1, 1. And we have two very nice functions called maximize and minimize, which will do that automatically for you. And there you are. It says that the maximum is at 2, 2, and the minimum is at 1, negative 1, just as we learned early on. But the closed interval method is the basic tool for finding maxima and minima on a closed interval. So as an application, let's take a business example. You have the cost function for a business, and the question is to find the number of units x that minimizes the cost. So what you do is you find the critical points, and there's just one over here. It's about 6,790. You plug in the critical point and the endpoints over here, and then what you do is you work out the values at those points, and you find out that you need to produce around 6,790 units to minimize the cost. So here's a plot for the problem, and you can see quite clearly that you actually do have a minimum somewhere around 7,000. So that's the end of this lesson. So let's summarize. So we certainly realize that optimization is a crucial component of our lives from day to day. Now, different people will use it in different ways. So for example, businesses will want to make the most money with the least amount of cost, while drivers might want to reduce the time that they take to go from one place to another. Now, the basic tool in this area is Fermat's theorem, which lets us find the critical numbers for a function. And the closed interval method is a complete method for finding the absolute maxima and minima. So that's the end of this lesson, and the next lesson we'll talk about the mean value theorem, a very important theorem in calculus. But before you do that, please do review today's lesson, look at the exercise, and make sure that you're ready for the next lesson on the mean value theorem. So thank you very much. I'll stop over here.